Okay, today the large language model for verification, a review, and each application in data augment. Abstract. This paper presents a comprehensive literature review for applying the large language models in multiple aspects of verification, including requirement engineering, coverage closure, formal verification, debugging functional safety, code generation and completion, and data augmentation. To demonstrate its capability, an experiment are carried out to automatically to generate a variant of the existing design and their verification code using a prompt. So the significant productivity and quality improvements are recorded and compared to traditional manual data preparation. Despite the promising advancement offered by this new technology, it's essential to be aware of the inherent limitation of LLMs and that lead to incorrect prediction. The paper cautions against using raw output of LLM directly in verification. In conclusion, three safeguarding mechanisms are recommended to ensure the quality of LLM output. Finally, the paper summarized the observed trend of the LLM development and expressed optimism about their broader prospective applications in verification. Chapter 1 Introduction. Language models are arguably the most essential types of machine learning models used for functional verification. This process involved handling the numerous forms of textual data, including specification and source code and test plans, test batches, logs, and report. And most of the textual content comprises natural languages and controlled natural languages or programming languages. Therefore, the effective use of the language model is critical for the application of AI/ML and functional verification. The development of the pre-trained LLMs are represented by a commercially available GPT 3.5 and 4 models and open source large language model Meta AI Llama series models have paved the way for the application of LLMs in EDA applications, and specifically functional verification. Some innovative researchers have included LLMs in their research and published existing results, which are summarized in this paper. The paper proposed a semantics approach to fine-tuning high-quality LLMs and showcases its use in data augmentation. Our survey and experiment also enable us to identify the three paradigms for effective LLMs integration in functional verification. Chapter 2 Application of LLMs in EDA software engineering and verification. Owing to novelty of the LLMs and search results for the application of LLMs in the verification have primarily been published within the last 2 years, while a few examples have focused on a broader area such as software engineering or EDA, and their findings are generally applicable to HDL as well. A. Assertion generation. Generating hardware design assertion, normally in system values directly from the natural language properties, has been extensively researched. Some previous research mainly focused on constrained natural language (CNL), a subset of natural language with the respective grammar and vocabulary to describe properties, and various rule-based or machine learning model-based converters are employed to CNL to predictable assertions. Learning a new language negates many benefits of such language. Due to a limited number of datasets available for training, this system performs less than ideally. LS2SVA employs LLMs to translate specification into intermediate representations based on the context of the design being verified. To ensure the quality of the result, a human-in-loop approach is introduced. However, no benchmark results are provided. On the other hand, the assertion generator described in 3 employs a syntax fixer to enhance the quality of the generated assertions. Examples are provided in each prompt in guide the LLMs in generating assertions. These assertions are then mass generated, compiled, and checked against the design using a simulator to evaluate their quality. The study reported that only 9.29% of the generated assertions are correct. However, the best combination of the various details prompt components contribute to 80% of all correct assertions, which demonstrated the importance of the prompt context, recovery closure. And simulation-based verification, tracking, and calculating code coverage can computationally intensive and time-consuming. Introduce the reference 4 introduce a curated data set specifically designed for coverage prediction for Python code. Each line of code is labeled to indicate each coverage status, executed, missed, or unreachable based on a given task. LLMs are then tasked with predicting the code coverage using the 0, 1, or multiple examples. While the accuracy of the line level prediction remains relatively low, ranging from the 20 to 30%, GPT-4 shows a promising result at a statement level. It achieved the accuracy of 84.47%, 90.71%, and 90.5% for zero-shot, one-shot, and multi-shot prompt respectively. While the results are derived from Python code, the general methodology is applicable to any programming language, including the HDL languages. However, it is expected that the prediction accuracy may be worse due to the relatively smaller representation of these languages used in training the LLMs. C. Formal verification. Formal verification uses mathematical models for formal methods to systematically validate the functionality and the reliability of the design against a specific requirement. Although the rigorous mathematics is not the strength of the open LLMs, Mandouh introduces a repair mechanism to generate a formal proof of the LLMs, and the proof repair mechanism incorporate error message from failed proof to improve the next prompt to LLMs. The experiment trained small LLMs with only 700 million parameters on natural language text and code and fine-tuned on proof. It demonstrated that it is possible to generate enough assertions to check the performance of the techniques. When combined with previous automatic providing tools, it can prove 65.7% of the theorems in extensive Isabelle and HOL benchmark. This achieved represent a new state-of-the-art result. Debugging. AutoFL is automated fault localization by providing a prior tailored test report to an LLM. Its performance on the defect4j benchmark is comparable to that of the classic state-of-the-art techniques. Notably, it has successfully identified 40% more than new bugs compared to the best classic approaches and ACC at 1. Additionally, the Rebel framework uses LLMs to generate a test using a few-shot approach based on the bug report. The LLMs are presented with the example bugs report and a test as part of the prompt and are tasked with generating a few test examples specific to the bug report in questions. These auto-generated test examples are ranked based on their likelihood of uncovering the reported bug before the actual test run. The test generated by Rebel successfully reproduced 33.5% of the all bugs in the benchmark dataset. E. Test stimulus generation. As a classic methodology, constraint random verification (CRV) is an important tool for hardware verification. However, generating the stimuli to hit the desired verification target requires years of experience and deep understanding of the design under test DUT. LLM for introduce a benchmark frame for the experiment to elicit tested stimuli with the LLM. It reports various levels of success depending on the complex of the duty. Cut coverage of 98.94% is achieved. 98.94% is achieved for primitive data prefetch core. However, the increase in the complexity, the result drops to the 86.19% for an IBEX CPU instruction decoder with a coverage rate of the merely 5.61%. It does not demonstrate any meaningful stimulus generation capability for a practical IBEX CPU design. Although better than the baseline, the CRV, its usefulness is restricted in a smaller scale designs and more unit level verification. Next section is the functional safety and security. DVAS uses the knowledge base embedded in LLMs to automate the entire workflow, starting from the vulnerability identification to mitigation with the security policy. It begins by identifying the security vulnerability based on the user-defined SOC specification, which are converted to the system value assertion SVAs after mapping them to common weakness entities, CWEs. A simulator is employed to evaluate the quality of the generated SVAs. The SVAs are successfully simulated are subsequently transformed into a security policy to address the identified vulnerability. This paper reports a success rate of 40% to 55% in generating relevant CWEs using the GPT-4 model. However, the success rate of the final policy fixes is not specifically mentioned in the paper. Section G is code generation and completion. The research represented in reference 10 introduced an experimental system that uses fine-tuned LLMs to generate Verilog code completion. To train these LLMs, the researchers collected a comprehensive training corpus consisting of Verilog code sourced from open source repositories and selected textbooks. The fine-tuned LLMs, which varies in size, demonstrate the impressive capability in generating compliable code for different levels of complexity. Specifically, they achieved a success rate of 98.7%, 72.8%, and 55.5% for basic, intermediate, and advanced problems, respectively. In comparison, the performance of open source pre-trained models is much lower, reaching only 24% in the best case scenario. The commercial Code Llama-002 model, on the other hand, achieves success rate of 84.7%, 45.2%, and 64.9% for the same test. Overall, the fine-tuned LLMs are able to produce functionally correct code 41.9% of the time, which is significantly better than the performance of Code Llama-002 at 35.4%. Chapter 3 is Design and Verification Experiment with Open Source LLMs. Due to the concern about the potential risk of IP leakage, many users of EDA software have chosen to most permissive open source LLMs instead of the publicly available LLMs. In this paper, we focus on evaluating the performance with open source LLM Code Llama 34 billion in large design and verification tasks. Section A, LLMs with mutation-based testing. Mutation testing is a technique to identify significant weakness or holes otherwise unnoticed in a functional verification test benches. A mutation is an artificial modification in the tested design induced by a fault operator. It changes the behavior of the tested design when a test set detects all the indeed mutations or kills the mutant. The test is said to be a mutation adequate. The proposed LLM-based mutation testing framework is illustrated in Figure 1. After extracting relevant design signals and variables and output, the RTL source code is scanned to extract a specific context candidate for fault injection. The LLM is then directed by a set of the prompt to change logical arithmetic bitwise and quality operators to generate a set of faulty versions of original DOT. A computer step is followed to assure the injected changes are synthetically correct. The mutation killing ratio is derived by comparing the simulation dump data of the original DOT and revised DOTs. Its values can be used to determine how many of the injected faults have been detected. The undetected cases are provided as a feedback to help direct a fix for the coverage hole in the test benches. Figure 1 is LLM mutation-based testing framework. Table 1 summarizes the experimental result on 3 in-house designs. 12 variants have been created for each design with 63, 69, and 1 and 5 injected test change ranges respectively. Among all LLMs generated changes, although 75% compile without errors, 25% still requires manual fixes. The test benches can detect an average of 40.49% of the injected changes only, and 49.41% were undetected by the current test bench. This exercise highlights the test coverage gap that should be fixed in the design test benches. These results prove the power of LLM in a mutation injection methodology to automate test bench hole identification. Table 1 is LLM change injection experimental runs. Section B, comparison design creation strategies. The other experiments are conducted to evaluate the LLM's capability to accelerate RTL design creation. Advanced prompt engineering patterns described in 12 are used to generate a high-quality prompt for experiment. A locally hosted Code Llama model is used to ensure the consistency and controllability. One may also need to introduce the LLM to generate code for follows certain coding guidelines that do not violate the subsequent linked checks. Both bottoms-up and top-down methods are evaluated in creating a simple ALU and CPU design from prompts. Table 2, LLM change injection experimental runs. Figure 2 is Bolt at the pipeline module generated with bottom-up creation. The bottom-up design creation starts by implementing small building blocks and it assembles them into larger blocks until the top-level design goal is achieved. Starting from the primitive multi-add module, more prompts are given to the LLMs to refactor the code to add more functionality. Some prompts are recorded in Table 2, so the generated Verilog was almost correct except that the output was defined as a wire instead of a reg. The LLM was able to correct it after one additional prompt reporting the issue. Notably, the generated Verilog code compiled without any errors or warnings as illustrated in Figure 2. So the top-down creation starts with the top-level, high-level design is instantiated or several building blocks, which is improved the new building block. So to design a new CPU module, the flipped interaction pattern is used prompting. It left to the LLM to discover the specs with questions. The creation starts with the first prompt. From now on, I would like you to ask me questions to create a new CPU and Verilog when you have enough information, or when I said when I say generate using the information you have, creating a Verilog module to model this new CPU. Ask me the question one by one. The prompt generated by the LLM are recorded in table 3. So the prompt 3 generated a flipped interaction for a CPU design. Answering those questions resulted in the creating various basic Verilog module for a selected CPU component, the ALU arithmetic logic unit, the register file and control unit, instruction memory and data memory. And finally, the LLM generated a Verilog module that instantiated the connect the house module. A module snippet appears in the following figure 3. The LLM is further instructed to make those different components more sophisticated using the refactoring techniques outlined in top-down creation. The generally top-level module compiles without errors, and warnings the sum gives the synthesis linked violation since the different instantiated components are added to the design. Those violations disappear once or smaller modules are added to the design. Figure 3 is a simple 16-bit CPU generated with a top-down creation. The C, design understanding and visualization. Another LLM application experiment is design understanding. The LLM capability in described Verilog code or text format is tested. The control operation example code generated from the various tests is recognized as an FSM by the LLM, which generates a graph language representation of an FSM diagram with a prompt. I need to visualize this control and underscore operation module using a graphics as a FSM diagram. The generated FSM visualization is almost correct from the first attempt as in figure 4, except for the logic of the loopback transition and the logic operators. One additional prompt on the LLM successfully fixed the errors. It should be noted that without specifying the type of the diagram, the LLM defaulted to generate a block diagram representation. So the figure 4 is a graphic visualization of the LLM-generated FSM visualization of control underscore operation module. Chapter 4. Paradigms of the LLM application for verification. The universal approximation in the theorem has demonstrated that artificial neural network ANNs can approximate the behavior of any continuous function within a specific range with arbitrary accuracy. However, the theorem also implies that the prediction errors are to be expected in most cases. The transformer architecture, which serves as the fundamental architecture for almost all LLMs, is not exempt from these prediction errors. Hence, it is advised that responses obtained from the LLMs should not be directly applied to the various verification tasks. Figure 5 is demonstrated for application paradigms that address the inherent issue of the prediction errors. In paradigm, and the additional knowledge is then accessible to the LLMs is used to create a quality gate or a guardrail, filtering out the unquality result. This knowledge can be in the form of the domain expertise to the specific rules related domains paradigm. Introduce a quality gate can produce feedback, such as error messages to the LLMs until the generated qualified result. This contiguous feedback loop allows for refinement and improvement over time. In paradigm C, an external agent capable of performing high-precision tasks is introduced to collaborate with the LLM. So the agent assists the LLM, the enabling focus to the task understanding and the orchestrations while delegating the accurate execution task to the agent. As evidence to the most research section 2, LLMs still struggle with the complex design and verification problems paradigm combines the programmatic approach together with the LLMs to tackle more challenging complex problems. It leverages a set of programmatic rules to address the complex problems represented to the LLM. So our experiment in section 3 have extensively adopted the chain of thought paradigm illustrated in D in either the top-down and bottom-up creation experiment to achieve satisfactory performance. Code chain proposes another change of thought approach to break the problem down into smaller problems and generate corresponding sub-modules with self-revision iteratively. The sub-modules are clustered together to generate a more generic and reusable implementation for each cluster. The last step involved re-implementing the original generated sub-modules with this generic implementation. It reports significantly improved the code modularity and correctness. For example, it fostered 61.5% overall correctness, much higher than the GPT-4's 34.75% or GPT-4 plus human feedback and self-repair 52.60%. The figure 5 is the LLM application paradigms. The section 5, the conclusion and LLM trend. Although the recent progress of LLMs for hardware design and verification (DV) has demonstrated promising progress, the reported performance and usability will lag behind the best achievable with the classic algorithm and methodologies. As most hardware design language HDLs are less presented in almost all open data sets, most LLMs trained on that cannot achieve the best performance for human design and verification tasks. During our experiment, we also encountered a few quirks in the LLM's behavior, including its struggle in following the instruction to capitalize keywords to generate synchronous set and inconsistency in data output. This behavior is expected as HDLs only represent a very small subset of the programming languages used in training most LLMs. So our analysis in May 2022 indicate that among the available GitHub repository, when most LLMs acquire the coding training data, only 0.5 kilo projects are written in the major HDL, Verilog system, Verilog and VHDL. However, 6.8 million, 5.6 million, and 3.4 million projects were written in more popular programming languages JavaScript, Java, and Python, respectively. Under representation of the HDLs in the training data also makes LLMs more susceptible to hallucinations and bad instruction following capabilities observed in the experiment. Much research has stressed the importance of data. For example, Verilog eval introduced an open data set that extracts 1 in 56 problems from the HDL pitch with automatic tests to validate the functional correctness of the LLM-generated answers. As reported by much of the research on domain-specific LLMs, a smaller LLM trained on a specific domain's datasets may outperform much larger generic models in the domain knowledge QA. The availability of more open-source LLMs in ongoing technology race against commercial LLMs has opened the possibility for fine-tuning high-quality LLMs using proprietary datasets. As a result, the design verification community has begun to leverage LLM to solve the verification problems. This paper provides an overview of current applications of LLMs in verification. So these versatile LLMs trained on general knowledge The demonstrated flexibility and emerging capability in solving complex verification problems within the studied applications. They complement the classic verification solutions and in some cases even outperform them. Our experiments have also shown a significant increase in the productivity for verification engineers during the design creation phase. So the survey, the experiment enabled us to summarize typical application paradigms rather than directly relying on the responses generated by LLMs, and various application paradigms should be employed to ensure the strict quality demand of the design and verification tasks in EDA. So there was chapter 6 with references. Okay, today I read this paper, Large Language Model for Verification, a review and its application in data augmentation, from DVCON2024. Thank you for your time. See you next time.